Hello. How is everyone? Good morning.
Good morning.
It's a very slow morning today. Is it midweek? So let's wait for everybody. Did anybody pay attention to the email I sent last night, or rather Canvas announcement?
Yeah, I already have Proctorio because we needed it for solids.
Okay. Was the experience, is that the one that was problematic at the very beginning, or what was your experience?
It was fine for whenever I did it because I took the test later. But I know
Okay.
the people that did it at 4 were the ones that had some problems. That took it like right whenever it started because they couldn't see the problems on
Did
Proctorio.
So did you, in that test, did you have to upload the scan of your?
Yeah, I uploaded it after.
Okay.
Like I closed and he had an assignment open where we could scan or turn in the scanned images of our test.
Okay. Well, what I set up, I don't know if anybody noticed, but there's like an assignment that says that its assignment is Proctorio practice. So basically, I posted a JPEG of the problem just to see whether you see it correctly. So there shouldn't be any downloading. Downloading is an issue if it's a linked file. Where your browser automatically goes and downloads. That's what's basically forbidden by Proctorio, because it could think that you're going online and downloading, or somebody sent you a solution and you're downloading, things like those. So basically downloading is a no-no. So I'm thinking like I create a question for every problem and post an image within Canvas. So there should be no downloading, but that's what I'm gonna test, like that you're gonna see at the other end. And literally you have to answer whether you see the image or not. So that's and then in the second two examples, I'm just like asking you, hey, write hello, Dr. Pradanovic, or something on the paper, and scan and send and upload as a separate file. And then there are some, like at the end, you can comment on what you think about the experience. So, okay, I'm back. It seems that my Zoom disconnected and reconnected. In any event, so what I mentioned is that I posted, I think now we have a lot of people signed on by now. So I posted information about Proctorio. If you've already used it, great. If not, now is the time to test that it works. And I actually do have a test, so you're going to get a sort of a dummy assignment, if you will, which is called Proctorio practice. And all you need to do is go and complete it in terms of like mechanical motion of what will be on the test. So in one example, I'm asking you whether you see the file correctly. I uploaded an image of the problem. Do you see that image correctly? That's literally the answer to the question, yes or no. And then the second two examples are you're on a piece of paper writing, hello, Dr. Pradanovic, showing that to the camera, and then scanning and uploading. So in that sense, oh, it seems that a lot of people got connected and then disconnected. Okay. Or rather disconnected and then connected. And then basically in that problem, you just have to practice and then scan it and upload it to the Canvas appropriate solution. And one thing that I'm asking you to do is basically to scan solution to each individual problem separately. So let me know if you have any thoughts about it, or you would just like to scan everything all together at the same time. Give me your opinion. It'd be easier on me if I had like every problem separate. Okay. Any questions about? I disconnected and connected again. I hope this is not a problem. It seems that
I think the connection is really bad because it keeps on like cutting in and out and kicking people off.
yeah, but the problem is that the connection related to Zoom, because I do see that it's happening to multiple people, so it's impossible that all of us have our own home internet connection.
Oh, okay. So it's a
Right?
Zoom.
I don't know. Like it seems multiple people. If it's multiple people, well, we are all in different locations.
It's true.
But I don't know. Like I'm sitting in the same spot in the same room and with the same internet connection that I always use, and I've had a number of issues in the past few weeks, but the internet actually wasn't one of them. So I don't know that. I don't know, but these things go. So you can't hear anything? Oh wow. Does everybody have an issue with hearing?
I can hear stuff right now.
Also,
For me, it's kind of cutting in and out.
On my screen, it says that when like you do speaker mode, Dr. Prodanovich, it says you have low bandwidth.
Huh. That is hilarious. Well, I can try to move to a portion of the house that typically that is closer to the router. That I can do. Nobody, unless my dog is like secretly on Netflix, nobody's like watching movies or anything in the house. So, Skylar, are you using a lot of bandwidth?
No, I'm just trying to turn off.
Because this is the first time I go in and out, in and out. This is like the third time. Okay, let's try this from my dining room. Well, let's give it a shot. If it really doesn't work for some reason, I will have to record a lecture separate and post it. But we'll see. We'll see. Let's try. So today we are, so before I start, since we've been disconnecting, so just one last a last attempt to communicate the message. So I posted Proctorio information. If you already have it installed, great. Then you just go and there is a Proctorio practice assignment that you will just go through the motions of what are you going to do on the test, so that I can test that I set everything up correctly. So call it beta testing, if you will, but if you complete it, which should be trivial, you're going to get full points and it's going to be like a quiz assignment. So why not? And that way we are then, if everything works out. So now I see again people going on and off. I hope see people coming in.
Dr. Prodanovich,
Yes.
when is the practice due? The Proctorio thing that you just mentioned?
Tomorrow night, but I can move that if that's a problem.
Okay, no, that should be fine.
Yeah.
I was just
So-
curious because we have a fluids test today.
Oh, okay. Yeah, tomorrow night, like Thursday night. I just want to have the information before Friday so I can address issues or ask you to do something else or whatever in class on Friday. So I'd like the things completed so I can look at them before class on Friday. That's essentially, that's where I'm going with it.
Can you
Because-
repeat how we're uploading like each problem? Is that after the Proctorio session or during the Proctorio session?
I'm thinking during, so I'm gonna allow for some time for that. But if that ends up being, because my intention is to leave an extra some time for basically that motion. If all fails, you just, whenever you scan, you email it to me. Does that make sense? And what I want you to do is, like, as you're for a certain problem or whatever, you can just show the pages like this. Oh, this doesn't, and apparently if you have a background on, then that doesn't work. But let me remove my background. None. Okay. So if you have a page, you just kind of show the page, right? So here's my page, and then basically you show me the pages that are going to be uploaded. So if I think that way I can verify that you didn't add 3 pages before sending it in. So then if you have issues scanning or that takes longer, you scan it, you email it to me, and if I think that there's anything wrong, I can just go and check, like, what did you show me on the video versus before the video completed. Does that make sense?
Yes.
So again, but this is gonna be a learning experience. So you're gonna actually, that's what this whole beta testing, that's how I think based on what I read, but I only read things so far on Proctorio. That's what I think is happening. So, but that's the whole point about all you need to do in this thing is write down, hello, Dr. Pradanovic, and then show it to me. And then go scan with, probably with your phone, or how are you scanning your homework right now? Maybe with your phone, maybe with some separate device, right? Are most of the people scanning with their phones?
Yes.
I have like a portable scanner that I use.
Okay. So then you're just gonna go, and then that's somewhere next to you?
Yeah, it's on my table.
Okay. So what I also want you for phone, so when you're basically testing or writing or whatever, I'd like that phone to be sort of somewhere in the view. So if that phone is what you pick up to scan, great. If not, I see that you're using a portable scanner device that is not. The issue that I'm checking for is, like, are you calling somebody else to, you know, discuss solution before sending it in, right? So that's what I'm checking for. We'll see. The cheating on exams in the age of Proctorio is going to be a whole new learning. So, I'm laughing, but I'm not laughing. I don't know what I'm up against. So learn as I go. Any other questions? Okay. So again, that's the whole point of doing a beta test, and you're going to get full credit for it. So just please go and complete. And if you have any concerns, let me know about the process, and any questions like this, what is happening. But that's, I think on Friday morning, we will all collectively be much smarter about it. Okay. All right. So let me start sharing my screen. Oh, okay. So some people are using just. So can somebody else try talking? Let's check the talking again.
Hello.
Okay. Did everybody hear James and Erlinda? Michael, I mean.
Ruben is texting me and Michael, and he's saying he can't hear.
So Ruben cannot hear again?
No.
Let me try just one more, because my microphone is on, but there are people who do hear me, right? So
Yes, I can hear you now.
Yes,
yeah.
I also.
So it's something with Zoom, because if somebody can hear me, then my microphone is working. And apparently, so it's something to do with the connection. That's all I can do. Good news is recording is recorded on my computer. So if my computer or microphone is working, that should be recorded correctly. Okay. So I apologize. This is the first time I'm actually having some more serious issues, technical issues with Zoom, which I guess is not too bad. Other than that glitch of mine where I didn't know where my camera was turned off, but that one was on me. That one was not on Zoom. Okay. We are starting mass transport today. And the related reading is in chapters 17 and 18. So a lot of things will actually sound familiar. We're going through the very similar motions that we had for momentum and heat transfer. And because of that, we will probably go a little faster than usual. So far, we looked into the transport of entire phase. You literally had an entire phase moving through. Let me just see. Okay, so everybody does see my screen? Just one more check.
I don't see it.
You don't see my screen?
I can see you, but not the screen.
Okay, let's try again. And now?
Yes.
Okay. So we're going to go through a lot of similar motions compared to momentum and heat transfer. So far, when we looked at stuff moving, we were looking at the homogeneous phase, or we were identifying, for instance, water as a phase, and just looking at the motion of water. Now, the water in itself is actually a mixture, and it could have multiple chemical species other than just H2O within. And diffusion is where we actually look at the movement of individual chemical species within what's normally taken as a thermodynamic phase. So they will then move from the region where there is a higher concentration of that species to the region of the lower concentration. I have some, again, messaging. I don't see chat. Somebody's trying to chat. I don't see the chat now, or it's not coming up. So one example would be if I have an imaginary separation between two types of chemical species. So you can see light gray species and black species here. And then I remove that separation, that imaginary separation, and let's say we have gas, then the molecules will start mixing and interdiffusing. So after the process is done, I had a very high concentration of species, gray species right here. And then after the process is done, I'm going to have sort of a homogeneous or equilibrated concentration of gray species throughout my medium. Now you can see how if I'm having multiple chemical species within, it starts getting extremely difficult to track down. So in any realistic problem, we're typically going to say, oh, I'm going to track species A, and everything else will be assumed another phase B, as opposed to separating it into 20 or so species that I might have within. Okay, so that's a typical way to look at this. So in everyday examples, you probably know if you have your favorite beverage in the morning, and if you're like me, you actually also need it to be sweet. So when you put something on the bottom of your coffee or tea in the morning, then suddenly you're going to have a higher concentration of sugar on the bottom of the cup. I actually use honey, and then as you kind of move up in the cup, you're going to have much lower concentration. Now, this is a relatively slow process, should I also say immediately. So we typically help it with a spoon, which is helping it with convection, right? to actually mix and equilibrate way sooner. If I just left it to the diffusion alone, I would be still sitting here in the evening and that would not necessarily be equilibrated. Similar example, now this is not necessarily my everyday example, but if you have a can of soda, you will be hard pressed to see me with soda. So if you have a can of soda and you open it, when the bubbles move up to the surface, it's CO2 that basically leaves that soda. And as the CO2 leaves the liquid and enters the vapor phase, basically in the liquid, I now have loss of CO2. And that basically pulls CO2 from anywhere else from that can, and that's why we get this upwards motion to the top interface. Basically, equilibration then starts to make up for the differences that have been done by some of the CO2 leaving. Okay, so again, we have like lower concentrations of CO2 in one place, higher in the other, and I'm typically moving to equilibrate that. Now, we consider here ordinary concentration diffusion, so basically only due to the gradients in concentration. It could be caused by all other type of gradients as well. And that's something that, like, by Fick's law, or what we will refer to as a Fick's law, we're just looking at the concentration differences. So dispersion and diffusion are same thing if we're talking about mass transport. However, in wave phenomena, you will hear that dispersion is separation of waves into different frequencies. If you're talking about mass transport, dispersion is the same as diffusion. So that's just disambiguating the common terms. As I mentioned already, diffusion is a naturally slow process. So if there is convection, it's typically dominating. And it will become competitive, though, on small length scale. So in porous media, we have clays. Clays have very small spaces in between. Let's say that I have clay platelets, and those pores are extremely small. Therefore, in those spaces, basically diffusion becomes competitive or on the same scale, length scale, or time scale as, as the convection in that material. And that affects mud rocks and shales. Now, we need a notation for all of this. And we're going to look at the, somewhat confusingly, things in two different ways, depending how they're specified. I could look at the concentration of mass concentration, which is the density as we know it. And we're going to, for species A, I'm going to refer to mass density as rho A, or maybe I will refer to that species as alpha. Then I'm going to say rho alpha is mass of all of the species alpha divided by entire volume. And this by V, we mean entire volume. Okay? And then for system, we know that what we typically call mass concentration of the entire phase, if I have two species or possibly multiple ones, then basically rho is mass of everything divided by V, right? So it's mass of A divided by V plus mass of anything else divided by V. I'm gonna call that else B. So basically my rho is rho A plus rho B. If I have two species, this is so-called binary mixture. If I have two species A and B. If I have multiple, I just keep adding them up. So this is sum of all of the components. Okay? So this is my mass concentration. Now I will work in mass fractions. So if I have that way, I'm in numbers between 0 and 1. So I can normalize my rho A divided by rho. So in this case, if I have only two species, my fraction omega A is rho A divided by rho A plus rho B. And if you actually plug in what rho A means, you will see that it's the same as mass of A divided by mass of A plus mass of B, okay? Because V basically factors out. And then nicely, if we divide this equation by rho, I will see that omega A plus omega B is always 1. And that is useful in all kinds of calculations. So this is for mass, defining mass concentration and mass fraction. We can do the same for molar. Okay, and a lot of times gases we're going to track in terms of molar concentrations. So molar concentration I'm going to refer to as Ca. Okay, this is supposed to be subscript A. So this is the number of moles of A divided per volume. So my Ca is in moles per meter cube as opposed to kilograms per meter cube. And C is equal to Ca plus Cb, similar as rho is rho A plus rho B. And then we have molar fraction. Xa is Ca divided by C. And Xa plus Xb is equal to 1. So again, we have mass concentration, which is denoted by rho, mass fraction, omega, molar concentration, C, and molar fraction, X. Rho, omega, C, and X. Those are sort of the new terms. And again, what's difficult about mass transport is not so much that the concepts are all that different. They're actually very similar. It's just the new terminology and a lot of it. At the same time, they're related in these using these relationships. So rho is the sum of all other rhos. All omegas sum to 1, all x's sum to 1, and C is sum of all of the other individual species, concentrations for individual species C. So it's this tracking of all of these individual species that sometimes makes these problems here. Okay. Now, the mass flux of, let's just move my controls. They're right when they're not supposed to be. So we are gonna also look at the velocity, of course. So velocity of species A is basically arithmetic average for all of the molecules in volume V, and I'm gonna refer to that as a vector VA. Now, I will also look at the fraction of species A, so this is a number between 0 and 1, times VA plus the fraction of species B or everything else times VB. When I sum them up, this is my weighted sum. I will get mass average velocity, and this is velocity as we are used to treating it for the entire phase. So when I multiply things by rho V, so this is my momentum. My momentum is rho A VA plus rho B VB, and you can do that by simply multiplying this equation by rho. Rho times omega A is rho A, simply by definition of omega A. Omega A is rho A times rho, divided by rho. Does everybody see how I get from here to here? And if not, I can write it down. Everybody okay? Okay, so basically by multiplying this equation by rho and substituting what does omega A actually mean, we will get that rho V, momentum of entire phase, is sum of individual momenta, which is something that I would expect from well-working definitions. So now the same thing, we just define it for mole average velocity. The mole and mass average don't always have to coincide. So my mole average velocity will have a star to it. So V star is XAVA plus XBVB, and CV star, sort of like molar momentum, if you will, is CAVA plus CBVB. Okay. So what is now our basic law for binary diffusion when I only have a simple case of concentration difference? We're going to go back to our parallel plates or our little slab. So assume that you have a slab of silica and there's some very simple gas diffusing through. So let's take helium. Helium is my species A that I'm tracking down. So on the lower end of this plate, I'm assuming that I'm keeping concentration, and this is now basically both concentration, the fraction omega A at some maximum possible concentration of helium in silica. So this is solubility. So this is the maximum I can possibly have in silica. That's called solubility. So this is where I'm keeping my concentration at that maximum. I have saturated silica with helium as much as silica would take. Excellent. And then on top of this slab, I keep this situation of no helium at all. So I might have a gas stream or like something literally blowing extra helium away that is diffusing through. So I can assume that at this boundary, I'm maintaining concentration at 0. Okay? So now if I let this system equilibrate, I can expect, as I normally get, that I'm going to have a linear concentration between this maximum on the bottom and 0 on the top. Okay, and I'm going to have a molecular mass flux of, since we are keeping this situation constant, or we're keeping these concentrations at the ends constant, so there will be a constant need to equilibrate them as well. So this is a steady state solution. So at steady state, I'm going to have a constant molecular mass flux of species A in this direction that I denoted as Y here. So what do I expect this to be? So I'm going to refer to my flux, meaning that I'm dividing by area. And so I'm not looking at just the rate in time, but also per area. So I'm going to refer to that as J. And the component of J in Y direction is this mass flux of A divided by area S. Okay. And I'm going to assume that that's basically just like in all other types of fluxes. It's directly proportional to this difference in concentration, inversely proportional to the separation between plates, which essentially gives me the differential, or what in the limit becomes derivative of omega. And then, so these are numbers that don't have units. And then I have also the overall density of the entire system that makes the difference, times what I'm going to refer to as diffusivity of A, which is my helium in this entire system. So everything else I refer to as B. So we're going to call that DAB. So when I take the limit of this slab basically getting smaller and smaller, I'm going to get that J, the Y component of JA, which is my molecular mass flux of the species A, is negative rho DAB. So this is now my coefficient of proportionality, but I do depend on rho because omega A doesn't have any units. D omega A divided by dy. Okay. Any questions so far? So this law has similar form as all of the other laws, Newton's law for viscosity, Fourier's law for heat transport that we've looked at. So basically it states that flux is proportional to the gradient of the what we call a driving force. So difference in the gradient of concentration. Okay? So my potential that needs to be different in places for anything to take place is concentration in this case. So if I have differences in concentration, I'm going to have diffusion. Okay? So if I now look at the 3 dimensions, I can look at this in every of the stated directions. So if I look at it in X, Y, Z, I'm going to get components in X, Y, Z directions that are equivalent. So technically, then my JA as a vector in 3 dimensions is proportional to gradient of omega A. So this is my gradient of omega A that has 3 components, and this is the coefficient of proportionality is rho DAB. Okay. So we need to, now that I have introduced the 3rd type of transport, we need to actually look whether which transport is dominant in the system. And what are the units of DAB? Can you work out the units of DAB from here? Take a moment. So again, mass flux. Whoa. We have mass flux here per area per time. That's on the left-hand side. We know rho. Anybody gotten anything? What are the units of diffusivity DAB? Stuart, are you there? What are the units? Anyone awake? Did anybody work? Should I wait for a couple of moments for you to work out the units of DAB? Victor, did you get anything? Hello? Adrian?
Harry posted in the chat.
Okay. Why not? I can't get to chat. Okay. Well, what did he post in the chat? Like I'm clicking on the chat and I can't get to chat.
Meters squared per second.
Excellent. That is correct. So basically, if I have here, I have kilogram per meter square per second. Okay. Rho is kilogram per meter cube, and omega is nothing. Doesn't have dimensions. Divided by dimension, the length or meter. So basically, that's going to give me meter square per second. Okay. So what else has in other types of transport? What do we have with meter square per second? What other coefficients? In momentum transport, which type of viscosity has units of meter square per second? There is that kinematic viscosity, nu, which I get when I divide the regular viscosity by rho, right? So sort of normalize it. So I can compare, for instance, kinematic viscosity, which is in meter square per second, and this diffusivity. I can also, if you remember, for heat transfer, we were actually comparing kinematic viscosity and alpha. Alpha was another diffusivity or normalized diffusivity, normalized conductivity, where I took the thermal conductivity and divided by rho and Cp. So basically, when I look at the ratios of all of these numbers, I get numbers that tell me which of the two that I'm looking at are dominant. So just like my Prandtl number was looking at the heat, at the momentum transfer versus heat transfer. Okay? Now we're going to have Schmidt number, which is momentum versus diffusion, okay? Or mass transfer. And we're going to have Lewis number that looks at thermal versus mass. Okay? So those are dimensionless numbers that tell me which transport is dominant out of the two that I'm looking at. All right. Now, one interesting part is that this when I'm looking at the mass transport, just because of the concentration gradient, I have to take out the motion that is relative to the entire phase. So I have something moving at overall velocity, but these concentrations equilibrating within, I'm looking at relative to that. Okay, so I don't want to necessarily always factor in the convective motion. So by definition, my JA is this. This is the momentum of my species A minus the convective part, like just motion with respect to the velocity of the entire system. And one interesting part is that I get then that JA and DA, JA plus JB. So if I have JA, oops. If I look at JA plus JB, so if I have two binary mixture of two, then I'm going to look at that is rho A VA minus V. So V is my motion of the entire phase, the average mass average, plus rho B of V B minus V. So I'm going to get rho A VA minus rho A V plus rho B VB minus rho B V. Now, what is by definition rho A VA plus rho B VB? If I go to the previous, so that's momentum of A plus momentum of B is momentum altogether, okay? And then minus, and what I get here is rho A plus rho B times V. What is rho A plus rho B? I put a lot of definitions in front of you today. So I have rho V minus rho V, which is a 0. So by definition, sum of all of these fluxes that are defined with respect to center of mass, when I sum them all together, I get 0 because of that. Okay. So again, rho A is defined with, this is the entire phase. And when I get all of these different fluxes, JA plus 0 in binary mixture. Or if I had more of the species, sum of all of their individual fluxes, because they're expressed with respect to the center of mass, there it's equal to 0. Okay. Now, interesting consequence for of that is that if I have I can also ask myself, well, okay, so I have diffusion of everything in all kinds of directions and counter diffusion. So if I have DAB, what is DBA? What is the diffusivity of species B in A? Okay, and so question is, what is by definition? So I can write the same definition for JA and for JB. So again, remember that I have rho DAB gradient of omega A. Oops. So basically, by definition, my JA minus rho DAB gradient of omega A. And now what we know for omegas, that all omegas together, they're fractions, so they sum up to 1, right? So by definition, since omega A plus omega B is equal to 1, then gradient of omega A plus gradient of omega B is equal to 0, right? So essentially, my gradient of omega B is minus gradient of omega A, okay? And that is minus rho dAB. And I'm gonna now put plus here gradient of omega B. At the same time, my JB, I know that JA plus JB have to be 0. So my rho DAB, gradient of omega B, and my definition of GAB is that it has to be equal to minus rho DBA, gradient of omega B. So that has to be equal to 0. And I actually have that it's rho DAB minus DBA. So what is DBA then? This has to be equal to 0, so my DBA is DAB. So however I look at the diffusivity, because of these relative motions, diffusivity of A with respect to B is the same as the diffusivity of species B with respect to A. Are there any questions about this? Whoops. All right. So take home messages that again, these fluxes are relative to the motion of the, relative to the center of mass and motion of the entire phase. And because of that, individual fluxes J, molecular fluxes as per Fick's law, they sum up to 0 when I look at all of the species and their individual fluxes. So that's the first message. And then also if I'm looking at A diffusing in B or B diffusing in A, it comes down to the same thing precisely because of these kind of symmetricity. Now, what are the example values? So this is in centimeters square per second, not in meters square. We can again see the different types of materials have different scales of diffusivity. So if I'm thinking of CO2 diffusing in nitrogen, then it's about 0.15 centimeters square per second. However, if I have liquids, ethanol in water is basically 4 orders of magnitude different. And then helium in silica, which is the example that we just looked at. So this is within solid. It's another 5 orders of magnitude slower. Okay, so out of anybody diffusing, gases will be the fastest. This is all assuming low concentrations of A. And you can find in chapter 17 of BSL, you can find the tables if you need a number for anything. In general, we have that the diffusivity increases with temperature. Whoa. And overall, we are looking at all of these problems at relatively small concentrations of A. Otherwise, we kind of get in trouble because a lot of these laws are not as simple and linear if the concentrations are large. So that said, diffusivity actually really always depends on concentration, but at low concentrations, we can assume that it doesn't. So it's not a big deal of it with low concentrations, but with larger concentrations, that fails. Okay. Now, the main message of the entire course is repeated. I have flux when there is a gradient of potential. And ultimately, we have these molecular mechanisms of all of types of transport, okay? And we're not going to go into kinetic approaches to actually explain them, but all of the origin of all of these transport mechanisms is molecular, and we use these coefficients to basically sum up that molecular behavior for different materials. So we're going to work with shell balances problems, and I'm here I should be able to work through all of them by the end of the class, but just in case, these are the good problems to work through in your textbook that are basically great examples of classical problems of diffusion. We're going to start with diffusion through a stagnant gas film. But before that, I'm actually going to work through equations of change, which are essentially a balance in itself. So let me, well, I have 2 minutes left. So I guess I'm just going to do that next time. And then we're kind of going to start fresh. Are there any questions? No? So by the end of this class, the sort of the hearing issue stabilize? I know I, for some reason, cannot bring chat into, oh, here it is. Okay. Has hearing problem improved? Over time? Yes, okay. Well, in any event, I will post the recording, so I apologize for the technical difficulties. I guess 1 out of however many classes. It's not terrible. It does happen. So I'm guessing something to do with Zoom because it was on and off. And it was kind of like good for some people, but not for the others. So that identifies to me problems with the software itself. Anyway, I will post the recording of the lecture right after the class. Let me know if you need office hours. I can stay on. Please do go try that Proctorio practice by tomorrow night. So on Friday, we know where we're at with mechanics of taking the exam. Okay?
Dr. Kardanovich, what material will be, or what material do we need to review for the test?
Essentially, porous media, momentum transport in porous media lecture. That's lecture 6. It's labeled as lecture 6 in materials.
Mm-hmm.
And then you will see that I skipped to lecture 8 because formally I skipped lecture 7 because of, well, you know what. So essentially lecture 6 in heat transfer, everything about heat transfer. So momentum transport in porous media and heat transfer, everything up including the last Monday. That's kind of always the rule in whatever I teach. So if the exam is on Monday, then what's included is up until 1 week before the exam.
Okay, thank you.
And I will not post any more homework before the exam. So the homework that was just completed is relevant and one before that. Now, as for practice problems, I do have in lecture 8, I have suggested problems in BSL from chapter 10. To basically, there are chapters that we didn't get to that are great practice. Any other questions? Okay. Well, if there are no questions, enjoy the rest of your Wednesday, and let me know. Well, stay on if you need office hours, or let me know.